Power. What is it? Where does it come from? How much do you need? Why can't we ever get enough? In this video, we will answer these questions and look at how power is generated. Energy or power is the capacity or capability to perform work. For a modern car to move down the road, it needs a certain amount of energy. But how much? That is dependent on the road conditions. A vehicle uses significantly less energy while traveling along a flat road than when it is attempting to climb a steep hill. There are two forms of energy, potential and kinetic. Kinetic energy is energy in motion, whereas potential energy is non-active. An excellent example of potential energy is gasoline. It does not exert any energy in its liquid state. However, when mixed with air and burned, it generates enough energy to power an engine. The burning or combustion of gasoline and air produces light, sound, heat, and pressure energy. The flame of the burning charge produces light. Sound is produced when the air-fuel charge is ignited. The combustion of air and fuel produces heat, and the pressure is caused by the quickly expanding gases. This pressure causes the piston to move down the cylinder. Let's examine how external forces can influence the motion of energy. If a car traveling down the highway is assisted by a tailwind, it will consume less fuel and the driver should have no difficulty steering. If the same vehicle is driven into a headwind, it will waste more fuel and be more difficult to steer. The conditions that affect the motion of energy are called variables. Horsepower. When trying to determine how much force a horse would need to draw a 330-pound weight, 100 feet, in 1 minute, James Watt introduced the term horsepower. We still use Watt's formula for horsepower today, which is shown here. In engines, force, or more accurately torque, is measured in pounds. The distance is measured in feet from the rotational center. The unit of time is revolutions per minute. Watt's initial computation of 33,000 was generated by multiplying 330 pounds by 100 feet, the distance and load a horse could pull in 1 minute. A dynamometer, or dyno, is used to measure horsepower. A dyno is basically a power absorption machine. To apply a load to a running engine, modern dynamometers use a water brake. As a result of the dyno being water-cooled, friction heat energy dissipates more rapidly, resulting in quite accurate figures. Engine horsepower is measured at the flywheel and is expressed in brake horsepower, or bhp. To answer the question, how much power do you need, multiple factors must be considered. Is the vehicle used for commuting? Does the vehicle operate in rough terrain? What is the vehicle's weight? Is it required to carry a heavy load? Is economy important? The responses will affect the design and output of the engine. Consider how much energy is required to power a commuter car. If the vehicle weighs 1,300 pounds and is expected to cover all sorts of different terrain, a 50 horsepower engine would probably be enough. However, if the vehicle weighs 4,800 pounds and must operate in difficult terrain, a 200 horsepower engine may not be adequate. A formula may exist to determine the horsepower for given weights and conditions, but when you factor in levels of acceptable performance, economy, and driving habits, that formula becomes exceedingly complex. The designers of racing engines are always in search of maximum horsepower. They devote a great amount of effort and resources to optimizing engine efficiency. Various devices, such as a dynamometer and a vast array of engine sensors, are utilized to continuously analyze the engine. Pressure, friction, and flow are constantly evaluated. They never stop refining the relationships between engine components. Combustion. Our discussion of engine theory will begin with internal combustion. It makes no difference if the engine is 2 or 4 cycle, piston or rotary based, spark or compression ignited. All are considered to be heat engines. All rely on the combustion of an air-fuel mixture in a confined space to generate power by applying force to movable parts. The most common unit of measurement for heat energy is the British Thermal Unit, or BTU. In thermal engine dynamics, scientists utilized BTUs to evaluate the gain or loss of heat. 1 BTU represents the amount of heat necessary to raise the temperature of 1 pound of water by 1 degree Fahrenheit. The amount of BTUs generated by different fuels varies. A gallon of gasoline produces about 115,000 BTUs, whereas a gallon of number 2 diesel produces more at 128,000. However, compressed natural gas, or CNG, only generates around 93,000 BTUs per gallon. As you can see, diesel fuel produces more power per gallon than either gasoline or natural gas. As a result, diesel engines produce more usable power per gallon than gas engines. Be aware that CNG requires 1.25 times more fuel to produce the same number of BTUs as gas. Gasoline engines can only convert so much fuel into power at one time. When more fuel is added, black smoke is produced, not additional power. The power output of diesel engines, however, increases with the amount of fuel used. But too much fuel can also harm engines. Engine efficiency. An engine's efficiency can be determined by how much gasoline it uses. Typically, a spark ignition engine needs half a pound of fuel to produce 1 horsepower for an hour. This is known as the BSFC, or brake-specific fuel consumption. For each increased horsepower, the engine will burn more gasoline each hour. Of course, using less fuel per hour also results in using less money. Increasing or decreasing the amount of fuel modifies the chemical compounds inside the combustion chamber. Gasoline burns at a rate of approximately 900 feet per minute. The air-fuel mixture of an engine does not burn from one end to the other, but from the outside into the center. This is due to the heat produced during compression and the heat radiated from the cylinder walls. Flame propagation is the process by which the air-fuel mixture is oxidized as the flame front expands from the flame kernel. The temperature of the combustion chamber, the temperature and thickness of the insulating carbon deposits that line it, the shape of the piston crown, the distribution of fuel within the air, the degree of turbulence and squish of the pressurized volume, the bore diameter, the geometry of the combustion chamber, and the location of the ignition source are all elements that affect the rate and uniformity of flame propagation. At 3,000 RPM, combustion occurs almost instantaneously, taking about 8 milliseconds. However, if the combustion process goes too quickly and the pressure peak arrives too early, this can result in excessive pressure, excessive temperatures, and unstable pressure pulses known as detonation. In other words, the pressure spikes when the piston is in close proximity to TDC, and it cannot go downward in the cylinder to release the pressure. Detonation creates a very brief pressure spike close to the peak pressure point and may cause an audible ping or knock. This phenomenon is like the more harmful pre-ignition. Pre-ignition occurs when something ignites the mixture in the combustion chamber before the spark plug. The charge can be ignited by a hot spot in the chamber while the piston is very early in the compression stroke. As a result, the engine spends a considerable portion of the compression stroke attempting to compress a hot mass of expanding gas. This obviously places enormous mechanical stress on the engine and transmits a huge quantity of heat to the piston crown and cylinder head. Component damage is almost inevitable. Air-fuel ratio. It is necessary for an engine to run at peak efficiency under varying loads. However, the fuel-to-air ratio will change significantly depending on whether the engine is idling, cruising, or operating at full open throttle. Air-fuel ratio, or AFR, is the proportion of air to fuel in the engine's combustion mixture. Most gasoline engines require an air-to-fuel ratio of 14.7 pounds of air for every 1 pound of fuel, or a ratio of 14.7 to 1. When an engine reaches this ratio, it is considered stoichiometric or at lambda. It may appear that stoichiometric is always the objective. That is not the reality. Typically, peak power is achieved with a richer mix, while a lean mixture improves drivability at cruising speed. Generally, idling is improved by a somewhat leaner air-fuel mix, but a large cam will idle better with a slightly richer ratio. Thermal and volumetric efficiency. The amount of air an engine consumes determines its power output. Its efficiency is measured by how much power it generates per unit of fuel consumed. Thermal efficiency refers to the link between heat energy and useful work. Those who work tirelessly to obtain maximum power from racing engines are well aware of the significance of air consumption to power production. There are numerous methods to boost the air/fuel flow into the engine or boost the volumetric efficiency. Some engines increase the number or size of intake and exhaust valves. The valve open duration and valve lift can also be increased. The valve ports can be enlarged or reshaped by machinists to improve airflow. Larger fuel jets on carbureted engines or modifications to the engine management and electronic fuel injection systems can be used to introduce more fuel. All this enhances the engine's power by maintaining lambda. The oxidation process. In order to transform the heat energy of the fuel into work energy, the air/fuel mixture must be oxidized or burned in a fraction of a second, typically only enough time for the crankshaft to rotate 145 degrees. In spark ignition engines, combustion begins when the spark plug fires and ignites a flame nucleus. This is referred to as the flame's kernel. During the combustion process, the flame kernel expands steadily and consumes all the air-fuel mixture within its reach. Multiple valve engines have improved airflow and air-fuel charge velocity. Using multiple valves has two possible advantages. Because the enlarged valve port area is larger than a single valve, more air-fuel mixture enters the cylinder, and the speed of the incoming air-fuel charge increases substantially, just as water shoots out of a garden hose with greater force when the nozzle is tightened. The modest increase in turbulence also improves the mixture of air and fuel. The end outcome is a more thorough oxidation. Engine designers have a difficult job. In addition to searching for power, they must also adhere to mandated fuel efficiency and emission standards. These variables are in constant conflict with one another. Increasing fuel economy and reducing pollution imposes limitations on power. Increasing power output increases both fuel consumption and emissions. Fuels. The most common fuel for engines is gasoline, which is derived from hydrocarbon-based crude oil and is fortified with a variety of additives. When converted to a gas, gasoline expands at a rate of 2,500 to 1. A single drop will grow to a size greater than a 2-liter drink bottle. Compare this to water at 500 to 1. When hydrocarbon fuels were eventually manufactured in significant quantities in the early 1900s, the majority of engines had extremely low compression ratios. Our knowledge of the internal combustion engine was in its infancy, and fuel quality was inconsistent. As engines grew larger and more powerful, improved refining methods were developed to improve fuel quality. As a result, certain spark ignition engines can operate at compression ratios as high as 15 to 1 and produce close to 4 horsepower per cubic inch of displacement. Engines with compression ratios of 9.3 to 1 or less can typically function safely using unleaded 87-octane fuel. Generally, engines with higher compression ratios demand fuels with a higher octane rating. The vast majority of fuels used in the United States are unleaded with octane ratings of 87, 89, and 92. Due in part to ever-increasing engine speeds, research into high-octane unleaded fuels is at an all-time high. Racing engines often exceed 12,000 RPM. This alone exceeds the maximum rate of gasoline combustion. Remember our 3,000 RPM engine's 8-millisecond burn time? Imagine the timing nightmares this creates for race engine designers. Ignition advance requirement. Spark ignition engines need a specific ignition advance. The number of degrees before top dead center, or BTDC, when the spark occurs. The maximum ignition advance of an engine can be found using a dynamometer. The distributor is advanced while the engine is running at the desired RPM until maximum torque is reached. At this point, to avoid detonation and accommodate for fuel inconsistencies, timing should be retarded a few degrees. An advance curve must be plotted to account for different load demands, such as idle, acceleration, and steady-state operating, because most engines must function across a wide range of RPM. It is necessary to consider the shape of the combustion chamber, the placement of the spark plugs, the density, and the temperature of the air-fuel mixture. In general, greater engine speeds demand more timing advance. This means you must have a mechanism that senses engine load requirements and adjusts the advance accordingly, but such a mechanism must be suited for all the variables listed before. The ignition map designed for one engine may not be compatible with another. Modern engines use an electronic spark controller to maintain ideal timing regardless of engine speed or torque demand. To ensure proper adjustment, onboard computers sample engine data 2 to 3 times per second. Some of these devices employ complex ignition maps. Spark plug location. In an ideal engine, the spark plug would be positioned directly over the center of the piston in the combustion chamber. The ignition would begin in the middle of the cylinder, allowing the flame front to move quickly without promoting detonation. However, because no two engines are alike, the ideal must be compromised. To identify the optimal placement of the spark plugs, it is necessary to understand where the hottest gas will burn first. For instance, the ideal plug location for an overhead valve engine is someplace close to the exhaust valve. The exhaust valve retains a substantial amount of heat from the exhaust cycle. In turn, this superheats the air-fuel mixture in that section of the combustion chamber. This superheating promotes the charge to expand and mix further. Another factor to consider when placing a spark plug in an OHV head is that the intake valve port must help cool the spark plug by directing part of the incoming air-fuel mixture towards it. A bad spark plug position might result in a rough idle as well as slow flame propagation during combustion. When choosing where to place the plugs, designers must consider the shape of the combustion chamber, the form of the piston crown, and the squish area. If the piston has a dome shape, the flame front will be interrupted when the piston approaches top dead center. Remember that our ignition occurs between 30 and 40 degrees before TDC. The squish or quench area is the space between the combustion chamber's flat surface and the top of the piston. The air-fuel charge is squeezed out of this area and into the combustion chamber's center. This is a nice bonus because the increased turbulence helps to mix the air-fuel charge even more. However, the heat of the expanding charge is quenched or cooled during this time period, increasing emissions measured at the tailpipe. If the plug is situated on the side of the cylinder, there is a greater risk of detonation. The cylinder in a spark ignition engine must be no wider than 8 inches and the plug must be centrally located. Dual ignition. Some overhead valve and overhead cam 2-valve engines use a twin spark plug configuration. Because the valve placements allow for the extra plug, it is especially well suited to those with hemispherical combustion chambers. The benefit of this configuration is that 2 simultaneously occurring ignition sources burn the air-fuel charge more quickly and more evenly. Of course, this gives you more power. Consider how quickly a piece of paper would burn if it was ignited from 2 different directions. Let's not get detonation confused with twin sparks from the plugs. Because both plugs burn at the same time and are in close proximity to one another, you won't hear the 2 flame fronts collide. Compression ratio. The compression ratio determines a substantial part of an engine's power. The compression ratio equals the swept cylinder volume divided by the combustion space volume. With low compression of the air-fuel mixture, an engine will use a lot of fuel to produce less power. Compression ratios must be consistent from cylinder to cylinder, which is crucial to remember during the engine building process. During the rebuilding process, the cylinder block and head are machined to restore a smooth surface. While only 15 thousandths or 0.015 inches of each component's surface is removed, these minuscule amounts can increase compression by 0.3 compression ratio points. With the additional piston displacement acquired from overboring, your compression may be increased by a full point. When the piston is at TDC, it normally does not reach the top of the cylinder. As a result, the volume of that area must be included in the compression ratio calculation. The cylinder head gasket has the same issue and takes up a similar amount of space. With so many variables in the calculation, a compression ratio formula must be used. Compression will naturally rise with simple rebuilding activities such as milling the block or head deck surface. However, you should not mill a block or head specifically to enhance compression because modern engine castings are manufactured to precise thicknesses in order to save weight. A more complicated solution would include significant cylinder overboring, increasing crankshaft stroke, or fitting specially engineered pistons to boost compression. When looking for maximum power, the piston crown and combustion chamber shape must be carefully chosen. Combustion chamber shapes. To increase combustion efficiency, combustion chamber and piston crown geometries are always improving. The combustion chamber characteristics will determine the engine's power, octane tolerance, and brake-specific fuel consumption. Because the piston is in constant motion, combustion does not occur at a constant volume. Therefore, the oxidation process should be completed as quickly as possible while maintaining smooth engine functioning. Turbulence is required to enable quick combustion, but too much can be detrimental, moving heat out from the chamber and causing noisy combustion. Turbulence is intentionally created and can be induced either externally in the intake port or internally with squish pads. The squish region is defined as the space between the cylinder head deck and the piston. It serves to cool the intake valve and should be placed close to it. The number of valves and the design of the valve train have an impact on the combustion chamber, including considerations for valve placement, size, and geometry. Other considerations include the material utilized and the position of the spark plug. As previously stated, starting the flame in the center of the bore allows for a faster, more even burn, resulting in higher cylinder pressure and fewer degrees of crankshaft rotation past TDC. Beyond emissions and octane tolerance, it is vital to have the cylinder pressure rise as rapidly as possible, allowing it to be used to expand against the piston for as much of the stroke as feasible in order to produce power. Because of its light weight, ease of porting and manufacture, and ability to dissipate more heat and allow for a higher compression ratio, most performance aftermarket cylinder heads are aluminum castings. However, because of its better thermal efficiency, a cast iron head is easier to create power with if all design elements are the same. To retain the same thermal efficiency while moving from iron to aluminum, the engine will require around 1 point more in compression ratio. This is due to the ability of cast iron to retain heat and use it to expand against the piston. According to experiments done by Chrysler in 1950, the hemispherical combustion chamber has the optimum surface-to-volume ratio. Compression ignition or diesel. Compression ignition occurs when intake air is compressed at extremely high pressures, frequently in conjunction with recirculated exhaust gas, producing the tremendous heat required for igniting diesel fuel, about 1,400 degrees Fahrenheit. Diesel fuel is injected into this superheated, compressed air and explodes. In contrast, spark plugs are used in gas engines to generate the heat required for ignition. Because fuel is injected directly into the cylinder or into a pre-combustion chamber, compression ignition engines require a different style cylinder head. Because most CI engines have compression ratios greater than 16:1, the combustion chamber is usually placed at the top of the piston instead of in the head. The piston may have a cone with a shallow bowl, or it may have a cone at the bottom of a small hole at the exhaust valve, depending on the design. Once the fuel is injected into the cylinder, the cone shape is needed to direct and mix it. The ensuing rush of expanding gases causes piston movement. This design can be used mainly in engines whose cylinders are smaller than 500 cubic centimeters. It is not well suited for cold weather starting conditions. Compression ratios generally fall within the 20 to 25 to 1 region. Engine cycle theory. As you might suspect, not all engines work the same way. However, we only have two operating systems. They share many similarities. Both work in cycles, which are commonly referred to as strokes. One design has 2 strokes, while the other has 4. The majority of producers have chosen to stick with a single system, the 4-cycle kind. Let's discuss how they work. 2-stroke engines. There are only 2 cycles in a 2-stroke engine, the power stroke and the exhaust stroke. Every time the crankshaft completes one complete revolution, or 360 degrees, the piston generates power. However, this is not as simple as it appears. The engine actually needs 4 cycles to generate power. The trick is that 2 cycles are happening at the same time. Because they produce power every time the crankshaft makes one revolution, 2-stroke engines provide a lot of power for their displacement, size, and weight. Needless to say, they are particularly thirsty and do not necessarily provide good fuel efficiency. 4-stroke engines. The 4-stroke engine has been around for almost a century. The cycles are straightforward: an intake cycle, a compression cycle, a power cycle, and an exhaust cycle. This is similar to the 2-cycle engine, with one major difference. To complete all 4 cycles, the engine requires 2 complete crankshaft rotations, or 720 degrees of rotation. Intake stroke. The intake stroke happens when the piston moves from the top to the bottom of the cylinder. This movement causes a pressure differential inside the cylinder. When a valve, in this case the intake valve, is opened, air at atmospheric pressure rushes into the cylinder. Compression stroke. The piston then begins its ascent back up the cylinder, compressing the air-fuel charge. During this cycle, both the intake and exhaust valves are closed. The cylinder's contents are driven into a small cavity known as the combustion chamber. If the air-fuel mixture is not compressed to a specific level, compression ratio, the engine's overall output will suffer. Power stroke. Things begin to move quickly in this cycle. When the air-fuel charge ignites, a tremendous amount of energy is released, driving the piston back down the cylinder. If everything goes smoothly, the full air-fuel charge will be oxidized during the power stroke. This is the one stroke that provides the engine's power. During the power stroke, both valves are closed. Exhaust stroke. Finally, we must remove the combustion byproducts produced during the power stroke. This is accomplished by the piston making another journey up the cylinder. The exhaust valve must be opened in order for the piston to push the exhaust gases out of the engine. The residual pressure from the expanding gases aids the piston in pushing the exhaust from the cylinder. Weaknesses and strengths. As you can see, 2-cycle and 4-cycle engines use the same processes. The 2-cycle engine produces a lot of power for its size and weight. Because it does not require valves in most circumstances, engine weight and the number of moving components are minimized. The main disadvantage of the 2-stroke is its insatiable thirst. It requires a lot of gasoline to run an engine that generates power with every rotation of the crank. Because this engine does not have a separate stroke for each cycle, a huge amount of fuel is lost. Remember that both the intake and exhaust ports are open at the same time. An efficient exhaust pipe can help to mitigate some of this. A 2-cycle engine can be extremely fussy if the pipe is not exactly to its liking. Emissions are also an issue because most 2-stroke engines require a small amount of oil in the fuel for lubrication. Oil does not burn well and emits a distinctive blue smoke. In general, a small displacement 2-stroke engine may create a lot of power for a small investment. The 4-stroke engine is more sophisticated. A complex cylinder head with valves and actuation mechanisms is required. The air-fuel charge must pass via passageways, manifolds, and ports, which requires changes to control airspeed and volume. The intricacy, on the other hand, gives us more control over each cycle. We can accurately modify valve piston timing to achieve more power while emitting fewer emissions. For decades, the design has been studied and modified, and it is still the engine of choice for the majority of vehicle manufacturers. The crankshaft and camshaft connection. Crankshafts and camshafts link the strokes of a four-cycle engine. In our earlier examples, we observed that each stroke was about 180 degrees apart. This is the gap prescribed by Nicholas A. Otto, whose 1876 Otto cycle engine was the first practical four-stroke. In reality, for maximum efficiency, the intake and exhaust valves must open sooner and close later than every 180 degrees. We can take advantage of scavenging by opening the intake valve earlier in relation to the piston at top dead center. Scavenging occurs when exhaust gases exit the combustion chamber and create a tiny vacuum. When the exhaust valve is opened earlier, the exhaust gases begin their journey outward sooner. At the other end of the cycle, the piston-created vacuum draws the intake mixture into the cylinder. If the valve is closed exactly at bottom dead center, the door will close too soon. By keeping the valve open a bit longer as the piston passes BDC, we can exploit the momentum of the air-fuel charge to pack even more mixture into the cylinder. The longer we keep the intake open, the more mixture we can cram in. There will be more on this later. A cylinder is typically filled after about 240 degrees of crankshaft rotation. Durations of at least 300 degrees are required for high-performance street engines. Depending on the nature of competition, all-out racing engines have durations ranging around 350 degrees. The piston continues its upward climb with the air-fuel charge neatly packed in the cylinder. It usually ignites at 140 degrees of crankshaft rotation, or 24 to 38 degrees before top dead center. This is a relatively brief span of the complete 720-degree cycle. Once oxidation begins, it is brief. The exhaust valve opens several degrees from BDC, allowing part of the pressure created during oxidation to escape. Once again, there is only a 140-degree span to move the piston and attempt to burn the full contents of the cylinder. If this exact timeline is not followed, the entire operation goes up in smoke, literally. The heat and quick expansion of oxidation supply our energy, but it also produces lethal combustion byproducts. The heat generated by oxidation must be dissipated. Exhaust gas temperatures commonly exceed 1,500 degrees, while the exhaust valve itself can reach 1,200 degrees. The exhaust has nearly completed its cycle when the intake valve begins to open. Overlap occurs when both the intake and exhaust valves are open for a brief period of crankshaft rotation. The degree of overlap is governed by the duration of the camshaft, which opens and closes the valves. When exhaust gases are hotter than 1400 degrees, they enter the exhaust manifold and eventually leave the exhaust system at roughly 250 degrees Fahrenheit. As exhaust temperature decreases, exhaust gas density increases. The dense departing exhaust gases generate a vacuum, similar to how water drains from a garden hose. A vacuum is formed in the combustion chamber if the intake valve is opened before the completion of the exhaust cycle. Remember that the piston is very close to TDC at this stage and serves as a floor for the incoming air-fuel charge. When the intake valve opens, the combustion chamber is virtually completely cleared of all exhaust gases. A little portion of the incoming air-fuel charge may be lost in the tube, but this is a minor trade-off for the greater benefit of higher cylinder filling. That is how scavenging functions. The more cylinders scavenging an engine can support, the more power it can create. In the next video, we will take a closer look at how to calculate the compression ratio. After that, we will start to investigate more complex engine components, such as the camshaft. If you liked this video and want me to create more content, please like and subscribe. You can also visit my Etsy store link to help me out there. Thank you. I hope you enjoyed this video.